In this video, we are going to discuss about the design of a built-up column with lacing system. Of course, in the previous video, we have seen similar problem. We have designed a single lacing system for a built-up column which is made with two C sections. సో రెండు C sections యూజ్ చేసి ఒక బిల్టప్ కాలం తయారు చేసేటప్పుడు సింగిల్ లేసింగ్ సిస్టంతో ఎట్లా మనం రెండింటిని కనెక్ట్ చేస్తాము అన్నది what we have seen in the previous video. In this video, we are going to discuss about the double lacing system. Okay, so how it is going to happen and how we are going to design the lacing system and connection. And in order to do that, I am considering 4 angle sections coming together to form a built-up column. So you are going to have 4 planes of lacing system. Okay, on all 4 sides. Angle sections, you know angle, what is angle section, right? So this is an angle section, L. So we have 4 angle sections as shown in this figure, and we have a lacing system 1, 2, 3 and 4 joining each and every angle to form a built-up column. So let me just go to the problem now. So design a built-up column, double laced column with 4 angles to support an axial load of 800 kilonewton. So he's asking us to design a built-up column with double lacing system, and this column, which is formed with 4 angle sections, should be able to take an axial load of 800 kilonewton. The column length is 14 meter, both ends are fixed, and assume Fe is equals to 410. Remember, both ends are fixed. These end conditions are very much important because we have to use effective length in our calculations. You know, effective length of a column changes with the end supports. If it is hinged or hinged at one end and fixed at other, or hinged at both conditions, or fixed at one end, free at other end. So this is how the conditions change at the ends of the column. Based on that, the length of the column is also going to change. Okay, so grade of steel is 410. If it is not given in the question also, you can take that grade of steel is 410. Of course, you know, Fe 410 grade of steel implies the ultimate strength of the steel is 410 Newton per mm square. And what is the yield strength of that particular steel? 250. So these are the values you can directly take even it is not given in the question. So let's go to the solution. So in this design, we have to go to 3 things. First one is the angle sections. First thing you need to calculate is the angle sections dimensions required. So he asked you that you need to use 4 angle sections to make this built-up section. So now you need to find out what should be the section, angle sections, what should be the length of its legs. Okay, both the legs. Okay, you have to decide by using the code book, so that the build-up section can be taking a load of 800 kilonewton. Next, lace a system for connecting all the 4 angles and perform necessary checks. So you know that these 4 angle sections are being joined with this lacing system, and you have to design this lacing system and also the connection. If you wanted to go for bolt connection between the lacing system and the built-up sections, angle sections, you can go to that. If you want to go for welding, you can go that. Okay, of course we will only consider only one of them. Okay, if possible both. But I think in the previous problem we have dealt with both welded and bolted condition. So you can refer that problem if you wanted to go for bolt connection instead of weld, or weld connection instead of bolt. The procedure will not change. Okay, so now let me jump into the first step, that is I am trying to find out what should be the sections required. So in order to do that, it's simple. Okay, first take what is the load onto the column that it has to bear. 800 kilonewton, that is 800 into 10 to the power of 3 Newton. Okay, four angle sections should be able to take this much amount of load. And we know what is that? Both ends fixed. Okay, both ends fixed. So what is the effective length? 0.65 L. Of course, you can get these values of effective length from the code book. And of course, I'm going to give the table of that for the different and conditions. What is the effective length at the end of this problem? So the effective length when the both the ends are fixed is 0.65 L. So length of the column is 14, length of each angle section is 14 meter, therefore 0.65 into 14, which gives you 9.1 meter or 9100 mm. So now we have to assume what is the value of design axial compressive stress. Actually, FCD is the notation for this axial design compressive stress. And now we use simple equation. What is that? PD is equals to FCD into cross-sectional area of built up column. Okay. PD is equals to FCD into cross-sectional area of the built up column. See, what is FCD? That is the maximum amount of compressive stress this column can take. I am assuming that value 150 MPa or 150 Newton per mm square. So why do we need to assume this value? Because in order to find out what is the section required from the code book, you have to find out what is the total area that is necessary, cross-sectional area that is needed. See this simple equation. You know what is PD? I mean, what is the maximum amount of load it should take? I mean, what is the load that this column has to take? What is that? 800 kilonewton given in the question. The column should take 800 kilonewton of axial load. So you need to find out what is the area required. From this area required, you are able to find out what is the dimensions of the section. But here FCD is also unknown. So unless I assume a certain value for FCD, I cannot get the cross-sectional area required. So I do this. And in some cases, what we do is we assume lambda. Okay, assume slenderness ratio of the column, and from lambda and Fy, you can get the value of FCD from the code book. Okay, so either assuming lambda and using that lambda and Fy to find out FCD, or directly assume FCD doesn't make any difference. Okay, when lambda is assumed, FCD is also not a correct value. It is also an assumption, right? Cross-sectional area is equals to 800 into 10 to the power of 3 Newton, that is the load acting on the built-up section, divided by the axial compressive stress FCD, which gives you 5333.33 mm square is the cross-sectional area that is required. Okay, so this is the cross-sectional area of the total built-up section. But you know that this total built-up section is actually being formed by four angle sections, right? So each angle system, how much should be the area? What should be the area? So provide four angles of area minimum 1333.33. I mean, this is simply 5333.3 divided by 4. Okay, so each angle section should have minimum value of 1333 mm square area. So from the code book, I found out that ISA 90 by 90 by 8 from table 3 of SP6 or steel tables. I have taken this section, and this section has an area of 1378 mm square. Okay, it is greater than 1333, right? It is the minimum value. So the angle section that you are taking can be equal to this value, or it can have area greater than this value. And next, from the codebook itself, I can find out the other parameters such as the location of the centroid of the section. This is the angle section, and this is the axis y, and this is axis z, and This is the centroid. So XX and ZZ, I mean YY and ZZ are the axis passing through the centroid of this angle section. So the axis YY is at a distance of CYY and axis ZZ is at a distance of CZZ. See, when this is called as leg, see, this is leg 1 and this is leg 2. So here, as you know, ISC 1990, that means this is the length of one leg and this is the length of one leg. So both the legs are of equal length. So దీని length ఎంత అయితే ఉందో ఇది ఎంత ఉంది. So for equal length of legs, the centroidal distance CYY and CZZ also going to be same. That is why CZZ is equals to CYY equals to 25.1 mm. What happens if I used a section ISA 100 by 90 by 8? The lengths of the legs are different, therefore CZZ and CYY are also going to be different. But here angle section has equal leg length. So RZ and RY, I mean radius of gyration about ZZ axis, about YY axis is going to be 27.5 and moment of inertia about YY axis and ZZ axis is 104.2 into 10 to the power of 4 mm power 4. It is going to be equal. So since I am using an angle section whose area is 1378, I am using 4 angles of such nature. So 4 into that value will give you 5516 mm square. This is the total area I am using. Of course, more than 1333. So now remember, you have to now calculate what is the actual FCD of the built-up column. So in order to find out the section necessary, I have assumed a value of FCD as 150 megapascal, but that is an assumption to calculate the section area. But now, as I know what is the area I am providing now, that is 5516, now I need to find out what is the actual FCD, that is the actual design axial compressive stress of the build-up section. I need to use the same equation, that is P is equals to FCD into area. So now I know what is P, 800 kilonewton, area I know. Now find out FCD. FCD is equals to P by A. P by A, 145 megapascal. So this is how I calculated the actual FCD. Okay. So now what we are going to do is, now you have to check. Okay. So what should I check is, this is it. So you have to check for the failure of the column for buckling and other issues. Okay. So let me just give you this. So from table 9C, okay, from table 9C, for Fy, that is 250, the grade of concrete, I mean steel, and FCD, we have calculated 1.5. You can find out what is the value of lambda. Okay, see from table 9C, from table 9C, you can get Fy, FCD, and lambda. These are the 3 properties that you see in table 9C. So if you know any 2 properties, you can find out the other one. So in this case, I know what is Fy of the steel and what is the FCD of the build-up column. So I can find out what is the lambda. So you know lambda is nothing but effective length by R minimum. So R minimum ante enti? So it is minimum of R YY and RZZ. But in this case, we have seen RZZ is equals to RYY. So minimum value is just RYY or RZZ. So just simply write R, radius of gyration. And effective length 9.1. Okay, but this is not how we find out. First, based on Fy and FCD, you find out what is the lambda from the table. So from the table, I found out that the lambda value is 74.36 for Fy 250 and FCD 145. But as I told you, that lambda is equals to effective length by R minimum. I know what is the effective length, right? What is the effective length? Actually, I have found out in the previous case 9.1, right? But here, remember, when we are using lacing system for the built-up section, the slenderness ratio has to be increased by 5%. So 5% increase చేయాలంటే I'm multiplying 9.1 with 1.05. So 5% increase అన్నమాట. So the effective length will be 9.555 meter. Okay, actually see, if from the lambda KL by R, KL increases, that leads to slenderness value alpha lambda also increases, right? So I mean, when you are using lacing system, the code is saying that you have to increase the slenderness effect of this column. Okay, that is for safe side. So now the effective length is 9.55, not 9.1 now. Okay, so use this value. So lambda is equals to effective length by R minimum. So R is equals to 9.555 into 10 to the power of 3, and in terms of mm divided by lambda value, I got R. But remember here, okay, this R is the radius of gyration of the entire built up section, not the angle section. That is to be noted. Okay, so you have to note that. Okay, see, generally the equation is lambda equals to effective length by R minimum for angle section, channel section, or any section. For built up section is also same. So if you put R minimum, R radius of gyration of built up section, you will get a slenderness ratio of lambda of built up section. If you put lambda of built up section, you get R of built up section. So since I have put lambda 74.36, that is the slenderness ratio of built up section, I am going to get radius of gyration for the built up section. This is not the single angle system radius of gyration. Okay, so as you can see in this previous step, the single angle radius of gyration of the angle section is 27.5. That is not we got here, right? Okay, this is of column. Okay, built up column. Okay, so now we have found out this R. So now what I need to do? So I told you that we are going to check for this column, and also the other important thing we have seen earlier is you have to find out what is the spacing required between each and every angle section. Okay, see, in this previous problem we have used two channel sections to build a built-up column, and I told you that it is important what is the spacing between these two channel sections. Okay, that is important, and that is denoted with S, and that is the spacing between the channel sections, which we found out. In this case also, you have to find out what is the spacing between the section, each and every section. Okay, so instead of this S, I mean, we have a little change in denotation here. Okay, you have to note that here. Okay, so let me go into this. So now, since R is equals to 127.76, I am finding out what is the moment of inertia required. So this is the radius of gyration, R 127. That is the radius of gyration that should be there for the build-up column. Okay, so from using this minimum R, you can find out what is the minimum moment of inertia required. So I is equals to AR square. Of course, you know this. And this is how you get this formula. R is equals to I by A. R is equals to I minimum by A. Okay, so I found out the value of I that is required. I know what is A, and R is calculated above. So this is the moment of inertia of the I section, of the built up section that is required. This is the I minimum. This moment of inertia of the angle section is same about ZZ and YY axis. Okay, but here we are talking about moment of inertia of the entire built up section. So if you see, this is the entire built up I section, 4 angle sections coming together, isn't it right? So now I should place these 4 angle section in such a way that the moment of inertia about ZZ and about YY is the same. Okay, so that is how we have done in the previous channel sections also. And the length of each side is denoted with S. Okay, see, from here to here, this is S. Okay, and this is the centroid. This is the axis through centroid. Of course, you have here, here, here. So the distance between the ZZ axis of the entire build-up section to the centroid of this section is Z. And from the centroid to here, it is CYY, isn't it? So now, what can you write this S as? S name and Raichu. See here, from this distance is nothing but Z dash plus CYY from here to here. But what is the remaining this? This also Z bar plus CYY. So if this is totally yes, so if S ఏమవుతుంది, S is equals to 2 times of Z bar plus CYY. Okay. So now if you find out what is the value of this Z bar, you can find out what is the spacing that is to be provided, isn't it? See, let me just go through that for you. See, we have found out what is the moment of inertia about YY and about ZZ. It is going to be same, right? Okay, we are placing these angle sections in such a way that this length is equals to S and this length is going to S. This is going to form a built-up section of cross section as a square, seems to be like a square. So let us find out the equation write the equation for moment of inertia about ZZ. So what happens for the equation? See, they are equidistant, right? This is Z bar and this is Z bar and this is Z bar. So what will be the moment of inertia? It is going to be I of each angle into 4, because you have 4 angle sections, into 4, plus the area of total angle section into Z bar square. Of course, you can find this in a different way also if you are confused with this. Okay, let me show you this. See, let us find out the moment of inertia of this first angle section. This angle section is here, right? This is how it is. It is at a distance of Z bar. So what would be the moment of inertia about this ZZ axis of this angle section? I am writing above here. See, what will be the equation? Moment of inertia about ZZ of angle section plus area of angle section into Z bar square. Isn't it right? So we have 4 similar angle sections. So into 4 multiply చేస్తే ఏమొస్తుందంటే we will get the moment of inertia about ZZ axis of the all 4 built up columns. Okay, all built up columns. But here you need to understand what is the value of, what is the reason for using this equation. We already found out what is the IZZ, isn't it right? 90.03 into 10 to the power of 6 in the above step here, right? We found out already here. But what is the reason writing here the equation is I'm trying to find out what is the Z bar value. So if I know Z bar value, I can find out the value of S. If I know S, I know what is the spacing that should be provided over here. Okay, so let me go through that. So I is equals to this value. So equate that equation with this 90.3 into 10 to the power of 6. You get Z bar as 124.76 mm. Remember, the angle sections we used are 90 mm by 90 mm leg length. Isn't it right? So right. So now, and this value is Z bar. And this total value is S. So now we know that S is equals to 2 times of Z bar plus CYY. I know what is the value of Z, so substitute that value. And what is the CYY? CYY is the distance between the ZZ axis, or of the built-up section, sorry, of the angle section, right? So that CYY, you substitute. We have got that from the previous step from the code book 25.1. So on putting it here, you will get S value 300. So what should be the side of each built up column? 300. So you already know what is the length of each leg, 90 and 90. So what is the distance between these two angle sections? 300 minus 180. Isn't it right? So 300, let me show you this here. So this is the angle section. This is 90. This is 90. What is this distance? This is 300 minus 90 minus 90, which is 180. 300 minus 180, 120. So 120 is this distance. But overall length of this side is S, which is equals to 300 mm. So since we found out the value of S from the Z bar, you have to calculate now the actual IZZ and IYY, because I have got something like this. 124.76 plus 25.1 will give you around what is the value? 124 plus 25, 150, and a little bit less than 150 into 2. So it is not exactly 300. It is going to be giving around 120, 294, 296. But I have rounded off to 300 mm. Okay. So since I have rounded off to 300 mm, I need to find out the moment of inertia about ZZ and YY once again. Of course, you are not going to find much difference, right? See, moment of inertia initially calculated is 90.03, and after rounding off the spacing, the moment of inertia is 90.22 into 10 to the power of 6. So in a way, you can just leave this step here, this step. Okay, no problem. Okay, you can just directly use this value as the moment of inertia. But the rounding off value of this S is very much high. Then, of course, if the value is something like 280 and you have considered 300, 20 mm is the distance you have rounded off. So you have to calculate the new moment of inertia of the built-up column in such a case. Okay, so I'm not going to tell you once again this step, explain this as you know earlier. So from this, if you calculated the actual moment of inertia second time, you will get the radius of gyration also again, which will be equals to 127.9 mm. Initially, the moment of, radius of gyration is something like 127.76, and 176 బదులుగా ఇక్కడ 127.9 mm. So not a big difference, right? And the slenderness ratio also. What is the slenderness ratio? Since R changed very little. Okay, so this is optional step. Okay, so now we found out in this first step what is the angle section that you need to use based on the area, and next you found out what should be the spacing between the two channel sections. Isn't it right? And you also tried to find out the revised moment of inertia and the revised radius of gyration and slenderness ratio. Since you know this lambda and Fy, you can find out the FCD of the entire section once again. The entire FCD once again. So you know that based on lambda and Fy, you can calculate FCD. So I calculated FCD for this section once again, because this lambda is revised, right? A little bit, even though it is decimals, just revise that. So FCD is 145.15 Newton per mm square. And of course, you know that design capacity of the section PD is equals to FCD into cross sectional area, 5516 into FCD, 800 kilonewton. So it is equal to the load that is coming on to this column section, build up section. So it is safe. So this is a check. This is a check whether this build up section is able to take this load or not. If this condition is not satisfied, you have to go for a higher angle section and you have to revise the previous steps. Now let me jump into this second stage in which we are going to design the double lacing system. So double lacing system. So you know how this double lacing system is going to be. So I'm not going in detail. So these are the two, this is the, let me draw this. So this is the elevation drawing and this is how the lacing system is. This is single lacing system, but double lacing system will be like this. Double. This is double lacing system. Okay. So as you know, this is the spacing between lacing. Okay. And other thing is, this is the angle theta, angle of inclination of this lacing bars, which is generally taken between 40 to 70 or 80, and we are going for 45 degrees. Okay. So the inclination of this slicing bars is 45 degrees and we are connecting face-to-face connection. Okay. So the connection, the built-up column is obtained by face-to-face connection of this. See here, this is the face. This is the face. This is face. And this is face. And this is back. Okay, this is back. So back-to-back connection ante ela untundi anamata. Of course, we do not use such kind of, but I'm just telling you what it means. So this is back to back. Okay, backs of each and every angle section are facing each other. If it is a face-to-face connection, the faces are going to face each other. So this is face, this is back. Okay. So now, so first of all, you have to find out what is the spacing between the lacing bars. As I told you, this, and this is denoted with L naught. So what is L naught? We have seen these expressions in the previous problem, so I'm not going to go through the equations, how we got this. So if you have any doubt how we got this equation L naught equals to a cot theta, you have to refer this previous problem in which we have discussed everything in detail. So theta is the angle of inclination of the lacing bars. A is the distance between the bolt holes, that is, which is obtained as A is equals to S minus 2G for face-to-face connection. So this is a face-to-face connection. Therefore, A is equals to S minus 2G. If it is back-to-back, then it would be different. You have S plus 2G. So on substituting the values, I get 210 mm. So the distance between each lacing bar here, this distance is L naught, which is 210 mm. And now see here, if you see this middle portion, this is the portion of the, what is that, built up column. This is the portion of the angle section that is a part of built up column, right? So it seems to be like a column of length L naught fixed at here and here, isn't it, right? It seems to be like that, isn't it? So because of the load, this portion L naught of the angle section has a chance of buckling failure. So you have to check, is there any chance that this portion of the column or the angle section between the lacing bars is going to buckle or not. Okay, it is very easy to find out. Let me just go through that. See, the slenderness ratio of L0 portion between the lacing is given. It should be less than 50. It should be less than 50. Okay, upon calculation, it should be less than 50, or it should be less than 0.7 times the unfavorable slenderness ratio of the whole column. Of course, you have found out what is the lambda of built-up section, right? So built-up section kuna slenderness ratio లో 0.7 కన్నా తక్కువ ఈ portion కి ఉండాలన్నమాట. Okay, so this is same. Okay, so let us find out what is the slenderness ratio of that portion. So what is that? Length by radius of gyration of that portion kada. What is the L0 length of the portion? 210 divided by the moment of radius of gyration. దేని వేయాలి? ఎంటైర్ built-up section కాదు. ఎందుకు అంటే see, this is the portion. If this is the L0 distance, even though this built-up column is formed by 4 angle sections, here this lacing system is being connected to individual angle sections, right? Angle sections ki connect chestam manam. So angle section yokka radius of gyration veyali. So 27.5. So upon calculation 7.64 or 2, which is less than 50. Okay, so first condition satisfied, and it also should be less than 0.7 times of the slenderness ratio of the intersection. Intersection slenderness ratio 74.25. 0.7 times of that value is 52. 52 kanda takkuva undi kada, very much less. So it is safe. So now you can say that the portion between the lacings will not buckle. So it is not going to buckle. You know how buckling happens, right? So let me show you that here in this figure once again. See, this column is going to buckle in the way. But since the slenderness of this portion is very much less, this portion of this angle section is not going to buckle. So we are safe. Okay. So now we found out two things now here. What is the spacing of the bars and what is the slenderness ratio, or checking the slenderness ratio of that portion. So now we have to go for the remaining part. What is that? You have to find out what are the forces that are developed in the lacing bars. Okay, so you know that this is a built-up section, this is the lacing bars, and there is a transverse force going to act. This is transverse shear force, which is equals to 2.5% of axial load. Okay, so 2.5% of 800 is 20,000 Newton or 20 kilonewton. So that is the value of Vt. So that is the value. That is the transverse shear force. So because of the transverse shear force that is acting on this built-up section, okay, this value is to be considered according to the code. In the code IS 800, in the clause 7.6.6.1, it is clearly mentioned this. Okay, please go through that. So now, because of this Vt, there are stresses that are generated inside the column's lacing system. So now, since the lacing bars are subjected to stresses, compressive and tensile, what happens is there is a chance for this lacing bar to buckle because of the compressive force, not due to tension force. So we have seen in the previous video that because of this Vt, some lacing bars are going to subjected to compressive force and some are subjected to tensile forces. So tensile strength of these bars is more than enough, okay, sufficient. But what happens is because of the compressive forces, these lacing bars can buckle. So you have to find out what are the forces coming into the lacing bars, and you have to find out whether the lacing bar is able to take that load or not. And the second thing you need to find out is this lacing bar is safe against buckling or not. We have done for this space portion between the lacing bars initially, right? So you have to follow the same thing here also. So we have found out that Vt, the shear force acting on the entire built-up section, and we also found out what is the shear force that is taken by each plane. There are two planes, right? As I told you, see, this is the built-up column. This is the lacing 1, lacing 2, lacing 3 and lacing 4. If a transverse force Vt is coming in this way, this and this plane is going to share this. And if a force is coming in this way, sorry, let me correct. Right. So this is L3 and this is lacing 1. So if a shear force is coming in this way, L4 and L2 lacing system is going to take that shear force. And if it is coming in this way, then this and this lacing system is going to handle it. So in any case, only two planes are going to share this shear force. Therefore, N is equals to 2. So number of shear planes is 2. So Vt by 2. So total shear force is taken by 2 panels. So each panel will take 10,000 Newton. So now the transverse shear load, this transverse shear loads will lead to the compression and tension in the lacing bars. So how is that value? What is that value is going to be? This is the expression, and 7 kilonewton or 7071 Newton is the force, compressive or tensile force in the lacing bars. Okay, so you need to find out the different dimensions now. What is the, so this is the amount of force that is coming into this lacing system. If this is the lacing bar, see the compressive force in this lacing bar is around 7.071 kilonewton. So ఇప్పుడు ఇంత ఫోర్స్ వస్తుందని నీకు తెలుసు కాబట్టి as you know, this much amount of force is coming onto this lacing bar, each lacing bar either tensile or compressive in nature. You have to find out what is the cross section required for the lacing system. What should be the thickness, what should be the length, and what should be the other dimensions. See, even though it is a lacing system, single lacing system or double lacing system, the procedure of solving this or designing this is same, and very minute differences are seen in this case. Okay, so now let us find out the dimensions of the lacing system, that is section properties of lacing bar. So let us connect the lacing bars by 20 mm dia bolded connections ki manam adopt cheskunnam. So according to clause 7.6.2, the minimum width of the lacing bar should be 3 times of nominal diameter of bolt, ante 60 mm minimum width undali. And what should be the thickness? See, what is the, this is how a bar is going to be, right? See here. Okay, so this is length, this is B, and this is thickness T. Okay, so this B minimum should be 60. And what is the thickness, minimum thickness according to 763? 1/60th of length of flat plate between bolts, that is A by sin theta. Once again, we have seen this derivation of these equations in the previous problem. Please go through this problem if you are not aware how this equation has come. The length of the flat of this lacing bar between bolts is A by sin theta. So which will give you 4.95, which will be rounded off to 6 mm. So width minimum is 60 mm and thickness is 4.95. We will go, sometimes we will go a little more than that or enough of that, same value. Okay, so we have gone for the thickness of 6 mm and width 60 mm, and the length L of the bar is 297 mm. So now you have to check for the slenderness ratio of the lacing bar. See, this is how this lacing bar is, right? Let me draw this figure completely. So this is how it is going to be, right? This is L. These are bolts. So this is this value. L. So there is a force here, compressive force. So now let us check what is the L value, 297 mm. So let's find out the slenderness ratio. It is same. The minimum, first find out what is the minimum radius of gyration of the lacing bar and its slenderness ratio check. What is R of this section? The cross section ఎలా ఉంటుందని దీన్ని చూడటానికి this is how. This is going to be width, which is equals to 60, and this is thickness, this is 6 mm. So what is the I value? I value is equals to B T cube by 12. And what is area? Area is equals to BT. So I by A whole root will give you T by root 12. Upon calculation, radius of gyration of this section is 1.73 mm. And from this, calculate the slenderness ratio. What is the effective length? See, the length of the bar, lacing bar is 297. It is fixed with bolts at both the ends. Okay, so according to the code, according to the clause 7663, the slenderness ratio of this lacing bar should be taken as 0.7 times of its length. So 0.7 times of 297 divided by radius of gyration 120. So the slenderness ratio of the bars, lacing bars, should be less than 145 in order to avoid buckling. So it is very less than 145. Therefore, there is no chance of buckling of the lacing bars because of the compressive force in it. And now find out what is the design compressive strength of the lacing bar, that is FCD. We found out FCD of the column section, built up section, but we are talking here about the FCD of the lacing bar only. So since we know what is the slenderness ratio of the lacing bar and what is the grade of steel, you can find out what is the FCD from the code book. So this is it. Of course, you know it belongs to type buckling class C. Okay, so you need to use table 9C. And so this is PD or P, FCD into cross-sectional area of the lacing bar, 60 into 6. Okay, this is the stress that this lacing bar can take, multiplied by area will give you the load it can take. See, what is the load? 30,060 or 30 kilonewton is the load that this lacing bar can take. So what is the load actually coming onto the lacing bar because of the transfer shear force? 7 kilonewton. So it can take way more than this 7 kilonewton, right? So it is safe in compression point of view. But I told you that when there is lacing system like this, in some there is compression, in some there is tension. Okay, so now what we need to do is we also check for the tensile strength of the lacing bar. So lacing bar యొక్క tensile strength will be minimum of TDN and TDG. TDN and TDG, rupture and gross area. Okay, so TDN is equals to 0.9 into B minus DH, sorry, into T into Fu by gamma M1. We have used this equation a number of times in our unit 2 and unit 3, right? So I'm not going in detail in this. So what is B? Width of this plate 60. DH, diameter of the hole. You know what is the dia of bolt, right? Dia of bolt is equals to 20 mm. And what will be the dia hole? Will be equals to 20 plus 2, 22 mm. So always add 2 for the bolt hole, right? So thickness 6 into remaining term Fu by gamma m naught will give you this. So now let us find out what is TDG and then compare this to take the least one. So TDG equals to Ag Fy by gamma m naught. You can find these expressions from your code book. You no need to blindly by heart this. So upon substitution, what is Ag? 60 into 6, this is not there, into Fy 250 divided by gamma m naught 1.1. So this is the value. So minimum of these two values, 81 and 67, what do you get? The 67 is the least value. So tensile strength is 67.3 Newton. Ante this much of tensile force it can take. What is the compressive tensile force that can develop in the lacing bar? 7 kilonewton. What is the tensile strength? 67. Ante దాని యొక్క ఎంతైతే దాని మీదకి వస్తుందో టెన్సైల్ లోడ్ దానికి 10 times దాని యొక్క స్ట్రెంత్ అనమాట. సో ఇట్ ఈస్ జస్ట్ సేఫ్. Okay, nothing is going to happen. Now you have to decide the connection. What is meant by connection? The joining of two members by any manner, by bolt or by weld, is nothing but connection. So what we are going to do is we are going to adopt this bolt as the connection, bolt connection. And you know what is the bolt strength? Okay, let me write this here. Bolt strength is minimum of bearing strength and shear strength of bolt. Shear strength of bolt. Of course, you have to check whether it is single shear or double shear. Ante oka shear plane unda, two shear planes unnaya. So in this case it is double shear because I am overlapping each other. See, this is the lacing system, right? So this is a lacing bar and I am overlapping this lacing bars. So cross section చూడటానికి ఇలా ఉంటుంది lacing bars. This is how it is going to look in the side view. Bolt is going to be like this. This is shear plane 1 and this is shear plane 2, double shear. Okay, there are two shear planes. So two shear planes అన్నప్పుడు formula into 2 into A and B into FUB by root 3. You can find this equation in this 10.3.3 clause. So on substituting these values, this is the strength of the double shear bolt in double shear. Next, bearing strength in bearing is given by this equation 2.5 kb fu into d into t by gamma mb. So you know what is kb? Kb is minimum of E by 3d naught or P by 3d naught minus 0.25 or FUB by FU or 1. What is E? E is equals to end distance and D naught is dia of hole, bolt hole, which is equals to 22. So upon calculation, one is 0.53, one is 0.51 and other is 0.98 and other is 1. So take the minimum value which is 0.51 and substitute this here and you will get the strength of the bolt in bearing is equals to this 50.184 kilonewton. So now what is the bolt strength? Minimum of those two values. So minimum and the 58. So now number of bolts is equals to what is the load that is coming on. See here, I am writing here. Number of bolts is equals to load coming onto this column, on this bolts total divided by strength of each bolt. So once again we have discussed about this equation 2 plus Vt by cot 45 in the previous problem. So upon calculation you get 0.28 bolt. So you cannot provide 0.28 bolt, right? So you have to round it off to 1 bolt. So now provide 1 bolt at each end of the lacing bar. See, as I told you, this is how it is going to look. Both these lacing bars are overlapping on each other. Okay. So now there are other things that we need to calculate still. What is that? So whenever we have a built up column like this, when we have a lacing system, either double or triple or anything single, you have to put tie plates at the top and bottom. Okay, at the top and bottom. Let me just draw this a bit better. See, this is the built up column and this is the so you have used a bolt over here and here. So this distance is small d, and this entire distance is capital D, and this small distance is E, and here also this is E. So you can see that capital D is equals to small d plus 2e and d. So what is small d? That is effective depth of the plate, and what is capital D? Overall depth. So according to clause 7.7.2.3, small d is equals to S minus 2 CYY. So upon calculation it is this, but you have to check that it should be greater than 2 times of the angle length. Angle length is 90. So 2 times of that value will give you 180. So it should be greater than that. It is greater than that. So no issue. And plus 2 times of E, edge distance, will give you D, capital D. So edge distance can be calculated. The minimum it should be 1.5 times of the diameter of the hole, that is 1.5 into 22. It is 33, and we have rounded off to 35 mm. So we have used 35, and based on the calculation, capital D is 300. So this has to be 300 mm. That has to be 300 mm. Now, what is the length of the plate? 300. Okay, we have seen, see, this is the angle section, isn't it? These are the angle sections. So type plate ఎక్కడి నుంచి పెడతాము? ఇక్కడ నుంచి type plate ఇక్కడ వరకు పెడతాం. Cross section, this is the top view. Okay, we have seen this is the S. S is equals to 300 for us. So that is what we have to put. And other thing is the thickness of the tie plate should be 1/50th times of length minus 2 times of gauge. Gauge is 45, so you will get thickness of the tie plate as 4.2 mm. Of course, you can round it off to 6 mm. 6 mm. And other thing is you have to connect this tie plate with the built-up section, right? So in this lacing system, when I'm using this lacing plate, use 6 on each side, right? So with the tie plate and connect with bolts of 6 number. So this is how this column, this is going to look. See, this is the tie plate. 1, 2, 3, 4, 5, 6. Each side 3, totally 6 bolts as shown above. So we found out what is the dimensions of the lacing bar and also the tie plate, and we also found out how many number of bolts are to be used for connecting lacing bar to built-up column. That is only one, but tie plate should be connected to the built-up section with 3 bolts on either side, total 6 bolts. Okay, and as I told you that I will give you the slenderness ratio values. This is from your textbook. See, this will give you restrained both ends and against translation at one end. This is the 2 ends, right? This is one end and the second end. See, restrained in both rotation and translation, and free, and one end fixed and one end free anamata. So I have wrote the general terms also. So please go through this notes. Okay, I'm just scrolling this so that you can see clearly in this video. Okay, so with this we have completed this design of this section, and these are few problem questions which are asked in your previous various examinations in the end semester and other exams. So you can just take a screenshot of this and you can just solve them. These are the questions which are asked for 15 marks or 14 and even for 30 marks. Okay, so take a screenshot of these problems. sides. Okay, you can just practice. While solving these problems, please take the previous problem which I have solved as a reference. These problems are a little bit lengthy, but that does not mean these problems are difficult to solve. So in the next class, what we are going to discuss is about battens. Okay, Batten connection. As I told you, this built-up angular sections are joined here by lacing system. Instead of lacing system, we have battens also, which are used to connect these angle sections to form a single built-up column. So we are going to discuss about the codec provisions and everything, and we are going to go into the problems also. Okay, thank you.